All right. Everybody awake? Good morning and welcome to this week of talks on this subject. We started at the School of Mathematics this, I hope it will be a tradition, of workshops on current events where we bring together some colleagues and try to work on a problem that's maybe hot and we are involved in it right now and hope to make progress on it. And there is this subject that I was started working with some of the speakers in the workshop, and we decided to meet here and give talks about this, and then obviously advertise it to anybody who wants to come, and lots of people registered. Of course, we announced that it will be live broadcast, and then some of them decided to watch it from home. You see what's more convenient. Anyway, before I start, I am wearing several hats. So the first hat is organizer. I have to give you some administrative information, and there'll be some probably other that I'll need to give you as we go along. So because we are a large crowd, we should go to lunch no earlier than 12:30. That's anyway the time that the morning talks are supposed to end. So if you're in this group, don't go to the lunchroom before 12:30 because other people know that they should go earlier if they don't want to stand in the line. What else? Coffee breaks. There'll be coffee breaks in the middle of the morning, and I mean between the two morning talks to afternoon talks. I had a cheat sheet of other things I needed to tell you. I guess transportation was supposed to, or parking was supposed to be a problem, but given that it's not so full, I guess I shouldn't tell you you have to carpool. Yeah, there'll be a picnic for all participants of the workshop on Wednesday afternoon after the talks end at 5:45 or 6 p.m. on Wednesday. Okay, so let me move on to the talks. As I said, this sort of project that encompasses some of the lectures that will be in this workshop started about 3 or 4 years ago in collaboration with Ankit Garg and Rafael Oliveira and Leonid Gurvitz. And since then, it's been sort of, I don't know, snowballing and diverged into lots of different directions. And what I would like to do in these 2 lectures, 2 introductory lectures this morning, is tell you about some of the motivations, and they are very diverse, some of the main results that you will see elaborated in many of the lectures in the workshop. And most importantly, I want to discuss the connections between different areas of mathematics that come together in this project. So before I start, I have to tell you about the P versus NP question, not just because it's the main goal motivating my field and me, but also because it will come up in a very direct way. And I often envy the physicists who have stars and galaxies in their picture, but I realize that I can do the same. You should just think of all these stars and planets as computational problems, and then you can think of P and NP as just 2 galaxies there. NP more or less captures the problems that we as humanity or computer scientists want to solve, or mathematicians want to solve or understand. And P is the class of problems that we can solve or understand. And given that computational problems are really capturing lots of scientific problems, mathematical problems, intellectual problems, this question of whether these two classes are the same is really a question about the limits of our understanding. So this is a P versus NP question in very, very high-level terms. We'll later see more concrete manifestation of it that will actually, part of this project is aiming at solving. Now, of course, we don't know how to solve this problem. It's a huge open problem. What complexity theorists do on a day-to-day basis is just try to classify different problems according to their computational requirements and resources they require, and classify them in various subgalaxies. And this is done mainly by devising algorithms, proving upper bounds on problems, and by proving lower bounds, by proving connections between problems. So this is the daily work of a complexity theorist. I want to take this opportunity to tell you about a book I put online a couple of months ago that talks about this and connections to mathematics. And the connection to mathematics is very important here, because I think that even though computer science and complexity theory are young fields, it's actually a very old field, and some of the most famous mathematicians worked pretty hard on both developing algorithms and on developing lower bounds or impossibility results or hardness results. And these connections, this existence of computation and computational complexity inside mathematics is part of the thing that will be manifesting itself throughout this workshop. Since I'm with mathematics and I want to tell you about all these connections that will be, many of these connections that we will see in this, during this week, I thought of starting with this very nice topic of the unity of mathematics. Mathematicians love to talk about this. They believe in it. They believe that different diverse areas of mathematics are connected, and every so often we see lots of surprising connections between areas that are not so obviously related. And I want to tell you about one additional brick in this in this proof how unified mathematics is in the projects that we are discussing now. And this is through the lens of a very simple object that is studied in lots of areas of mathematics, simply a collection of matrices. So I'm going to tell you about 6 areas of mathematics, and in them 6 problems, one in each, that arise more or less independently and naturally. Some are fundamental in these areas, some are just natural. And they are all related, and their relationship will be unraveled in this, during this week. Now, you don't have to understand them all now, because I'll talk about them more later, but I just want to impress you with the diversity of these problems. So all problems have as their, let's see if this works, have their object of study a tuple of M matrices, n by n matrices over a field. Okay, you can think of the field as the rational numbers. And I'll just define these problems, run through them, and then I'll tell you about their relationship. I just want to, as I said, impress you with the diversity. So you can think of linear algebra, these matrices are linear maps, and you can think what happens. One question you can ask, is there a subspace that all these linear maps together take into basically shrink into a subspace that's smaller dimension than the original, how does this work? Yeah, than the original one. Some of redundancy of this map. So that's one question in linear algebra, a very basic question. In arithmetic complexity theory, you can think of a tuple of matrices defining a polynomial in the following way. Think of having n by n matrices of variables here, and consider this determinant, the determinant of some of this tensor product of ai and xi. It's a large matrix, n squared by n squared matrix. You take its determinant, it's some polynomial, and the question is whether this determinant is 0. It's another property of a tuple of matrices. Oops. I can control this very well. Very different question. Here's another very different question. A tuple of matrices can represent what's called in quantum information theory a completely positive operator, completely positive map. It just acts on matrices P using this formula. So that's how a tuple acts on a matrix. And another very different question is to consider what is the relationship between the output of the operator and the input of the operator when you look at their determinant. How small can it be? How small can this be? The question is whether it can be as small as 0. Okay, another very different question. Let me continue. In non-commutative algebra, you have a bunch of non-commuting variables. It turns out, and we'll see it later, that tuple of matrices can represent rational expression, just expression in non-commutative variables. And the very basic question, non-commutative algebra, is whether such an expression is 0, right? Whether this is identically 0. That's basically the word problem of this. In this algebra. So again, a very different question about the same object, tuple of matrices. In invariant theory, it turns out that the tuple of matrices can represent an orbit under a group that acts on them. The group just changes bases on the left and on the right. And you can ask the question of whether this orbit, when you consider its closure, contains 0, whether you can push all these matrices simultaneous to 0. That's a basic question, the null-con problem in invariant theory, another question about this tuple. And finally, an analytic problem, you can consider again these matrices as linear maps. And I don't expect you to follow this expression. You can ask whether a particular analytic inequality, multilinear inequality, holds for every function from Rn to R when you apply to this, when you apply these linear operators to the variable you integrate over. So don't worry about understanding this. This is a statement, or this is a question underlying the Braskamp-Libby inequalities, and just to connect it to something you know, a very special case, a very, very special case here is a Cauchy-Schwarz inequality. Anyway, this bunch of problems look completely different. They are from completely different areas, and I'll say they are related. And in fact, this relationship is sort of stunning. They are the same problem. They are all the same problem. So following, this is not new. These are, follows from a lot of results for a century or a bit more. The first 5 are exactly the same, just exactly the same. The answer is yes to one, exactly when it's yes to the other. And the 6 is almost the same. And in particular, because they are so related, these relationships will be used in the work we do. And in particular, when we derive an algorithm for one, we derive an algorithm for all. And this will be well, a starting point. The work that started all this is that we can show that all these problems can be solved in polynomial time. So this was like a summary of these connections, and now I'll start elaborating. Key to all these connections will be the use of symmetries, and that's an invariant theory connection, and of course, the algorithmic aspect. So, by the way, stop me if there are questions. Okay, so what I'll do, I'll define the problems, and I'll define the background to these problems, and then I'll talk about the algorithms. I'm going to start with what will be the toy problem of the real problem we want to solve. It's called the bipartite matching problem. I'm a bit anemic, so I'll have to sit down part of this. Perfect matching problem is a basic combinatorial optimization problem. We have a bipartite graph, and we want to know whether we can match the left vertices to the right vertices. This is a good manifestation of this problem for those with kids. Not every kid likes every candy, but in this case, we can match them with candies they like. In other graphs, it's not possible. So in this graph, there is no perfect matching from the left to the right. And the basic problem is given a graph telling which is the case. It's a combinatorial problem, and a lot of the important connections will come from making it algebraic. And an algebraic way of representing it is by looking at the adjacency matrix of this graph, let's say of G. So we put 1 if there's an edge and 0 if there's no edge. And we ask, what are we asking? Perfect matching here really asks whether the permanent of this matrix is 0 or not. What is the permanent of a matrix? The permanent is just like the determinant, which we'll soon see again, only without the sign. So we just sum over all diagonals, products of the diagonal entries. That's the permanent. So a graph has a perfect matching if and only if the permanent is positive. And another mathematician who indulged in algorithms, Jacobi, more than a century ago, showed that this problem is in P. It gave a polynomial time. Was probably after Euclid's GCD algorithm, I think it's the first non-trivial polynomial time algorithm. He was interested in it for reasons of ordinary systems of ordinary differential equations. Anyway, this has a non-trivial algorithm. And we are going to look at, and this is taught in every computer science class, and we will look at different algorithms for this problem. And this will be the key to the algorithms we later develop for operator scaling. Yeah?
The question is to know if there is a hard thing or to find.
Both are interesting, and at this point, you can, this is a decision problem, and you can ask both. Both can be solved. It's easy to see that you can, if you have the decision version, you can solve the search version, because then you remove an edge and ask whether, you still have a matching, and you can pick the edges one by one. Yeah. So now we are coming to the real algebraic connection, and this is an amazing sort of visionary question by Edmonds, or connection by Edmonds. The permanent polynomial, as we'll see, is a very difficult thing to compute. The question is whether it's positive or not is easy, but whether to compute it is hard. And he was trying to connect it to the determinant. So let me explain how Edmonds did that. He said there's another way to make the problem algebraic here, and then by constructing another matrix in which we replace the ones by variables, by independent variables. If you have a 1 in ij position, you put there xij. And now look at this matrix. It's a symbolic matrix, right? And ask whether this determinant, the determinant of this matrix, which is now a polynomial, vanishes identically. Okay? Now, it's clear that this vanishes identically if and only if this has a perfect matching, because if you have a diagonal that's non-zero, it will never be cancelled with another diagonal. So it's easy that this problem is still the same perfect matching problem, and the leap that Edmonds did was this one. He says, well, okay, why only consider matrices with single variables in their entries? Let's allow arbitrary linear forms in some set of variables in every entry. And again, we can look at, so right, every entry has a linear form sitting in it. And so you can represent this matrix just as a formal sum of ai xi, where ai are matrices in the field. And you can ask the question, is the determinant, which is again a symbolic polynomial, is it identically 0 or not? That's a problem. Okay, so it's the same problem as before, but it's applied now to a general symbolic matrix where every entry is a linear form in some set of variables. And I should remind you that you cannot expand the determinant, or you can, but it will take you exponential time. So an obvious solution is not going to work efficiently. So what do we know about this problem? This was introduced 50 years ago. This will be the key motivation for this project, and we don't know how to answer it. I call it the singularity problem, whether this symbolic matrix is singular. It's also called PIT, we'll see soon why, polynomial identity testing problem. So what do we know about this? He asked whether this has a polynomial time, deterministic polynomial time algorithm, and Lovász observed that it has a very simple probabilistic polynomial time algorithm. Basically, plugging random numbers into the variables will do the job. I'll say it again in a little more detail. So you might think this is really the object of, I'm saying it's important, that's what we seek. It's, why shall such a particular algorithmic problem be so interesting? Well, it has two reasons. One is the discovery of Valiant, that this problem is actually a very general problem. It captures, this singularity of determinant captures essentially all algebraic identities. Again, I'll elaborate on that. We knew it in many ways because the singularity problem is, captures, one way to look at it is whether a space of matrices, this linear space generated by the AI, what is the maximum rank, what's the largest rank of a matrix in this space. And there are many special cases of this all over mathematics. When you see this icon of a cool guy, it means that there is a cool talk happening in this during this week. Roy Meshulam will tell you about this combinatorial geometric aspects of this space of linear matrices. This was one reason why this problem is important, but really the sort of the hammer that hammered it in was a result about 15 years ago by Cabanes and Impagliazzo, saying that if this algorithmic problem, which already has a probabilistic polynomial time algorithm, has a deterministic polynomial time algorithm, if we found a deterministic polynomial time algorithm, then we proved something like P is different than NP. I'll explain this quote shortly, but I want you to stare at it because it's sort of amazing. What's amazing here? We are the P different than NP means that we are proving hardness of some problem, right? Some problem is hard. And the way it is being proved is by giving an algorithm to another problem. This kind of connection is, we knew similar ones, but this is one of the most stunning examples. And I'll soon explain it in more detail, in particular what the quotes in this inequality. So that's really the reason we want to solve symbolic determinant. Okay, so let me tell you about that. So I want to just take now a detour, and there'll be lots of detours in these in two lectures into various fields, and you'll get a glimpse of them. Here I'll take my time, others will be shorter. I want to give you a little short tutorial of arithmetic complexity theory. So we'll talk about VP versus VNP and determinant versus permanent. So the basic question in arithmetic complexity is, going back to second grade about addition and multiplication. What can they do? Well, in variables, they compute polynomials, and the question is, how cheaply can you represent a polynomial? So here's a particular polynomial. If you expand it in terms of monomials in the usual way, you get a representation, the natural representation of this polynomial. But this representation takes exponential size in the number of variables, right? So that's one representation. Of course, the other representation is just the way it was given above, just as a product of sums rather than the sum of products. And this is far cheaper. This takes linear size. So the question we'll be interested, or arithmetic complexity theory is interested in, is what is the cheapest way to represent polynomials and to compute polynomials. So let's define it. We'll care about polynomials and rational functions. So the way we are representing polynomials is either by formulas or circuits. We basically take the variables and then feed them into a computation that is allowed to add and multiply the variables and any field, any constants in the field you have. And out comes a polynomial. And the question is, what is the smallest circuit size? What is the size of smallest circuits computing such a polynomial for a given interesting polynomial? That's a fundamental question because we are interested in computing polynomials. We'll be interested also in circuits with division, but let me not worry about this now. And so we, like with P and NP, when we talk about Boolean computation, also when we talk about arithmetic computation, we define the easy polynomials, those that have cheap representation. Those are called VP after Valiant. All polynomials for which the representation has the polynomial size in the number of variables and the degree, which we will take basically to be also n. So these are the easy polynomials. So what are the hard polynomials? Which polynomials are easy? The VP versus VNP question is a question like the P versus NP question is, can we efficiently compute everything, all polynomials we care about? So if we look at all polynomials, let's say of n variables of particular degree, here is the easy polynomials. And we know, of course, we know very many ones that we can easily compute, the symmetric polynomial, elementary symmetric polynomials, Fourier transforms, matrix multiplication, determinant, and so on. And there is a vast set of other polynomials, and the question is whether all are easy. And the answer is, of course, not, because just counting arguments. If you take a random polynomial, we just do a counting argument, it's clear that most polynomials are not easy to compute. But on the other hand, do we really care about them? Do they arise naturally in mathematics? And what are the natural polynomials? So Valiant was audacious enough to define them. He defined them. He defined the class VNP. He didn't say it, but I'll say it. These are all the interesting polynomials there are. There are all the interesting polynomials mathematicians made up. They all sit in this class VNP. They include all the polynomials that arise in, that we know of, that arise in algebraic combinatorics, for example, for enumeration. There are all the polynomials that arise in statistical physics, in partition functions. And a particular interesting polynomial there is the permanent. And I'm not going to define VNP, but as you'll see, I will not need to. And the reason is that in complexity theory, we are lucky to have classes of computational problems represented by very specific ones. And here, VNP will be completely captured by the permanent, and VP will be completely captured by the determinant. So let me tell you about them. We saw them already. So these two polynomials are, the input to them is an n matrix of variables. And here are the formulas that they are very familiar with. And they look almost identical except for this sign. And there are many things similar about them. They're homogeneous, multilinear, degree n polynomials on these n-squared variables with simple coefficients. Of course, you should take a field not of characteristics 2, because then they are the same polynomial. And they basically look like twins, but they are about as twins as Schwarzenegger and Danny DeVito in this movie. They are very, very different. And that's basically what Valiant showed. He showed that, on the one hand, determinant completely captures all the easy polynomials, all the polynomials in VP. And the permanent captures all the polynomials in VNP. And what do I mean by capture or by complete? Again, I will not formally define it, but I'll soon demonstrate it. Just affine projection. For example, the statement that determinant is complete for VP is just a statement that every small arithmetic formula or arithmetic circuit is a small symbolic determinant. Can be represented by a symbolic determinant of the same size. And for the permanent, it's the same. Every polynomial in VNP can be expressed as a symbolic permanent. So if we want to understand whether P equals NP, it's sufficient to know whether we can represent the permanent as a symbolic determinant that's small. So to answer this question, we just have to know whether the permanent has a small symbolic determinant. And this question arose sort of independently, just out of curiosity, by Polya. So let me say again what it means by a projection. What do I mean by represent? I'm given a matrix X, and I want to compute its permanent. The question is, can I write another matrix, maybe a little larger, K by K matrix, put in its entries linear forms of these variables, compute its determinant, and out will pop the permanent of the original matrix. Okay? That's an affine projection. This is a projection. And the question is, how small can I make this K? And as I said, this question arose out of curiosity by Polya. He noticed that the permanent of a 2 by 2 matrix is easily a determinant of another 2 by 2 matrix, right? You just switch this sign. But he also observed that it's already false for 3. So what's going on? And it's not, in fact, if you think about it, it's not even clear that there is a finite K that will do the job. This, in fact, follows from Valiant's completeness of the, well, both of the permanent and the determinant, that there is a bound. There is at least an exponential bound on this. And also follows from what he proved is that P versus NP, VP versus VNP is exactly the question of whether we can have such an affine projection, which is polynomial in blow-up only. And if you wonder what's the best that we know so far, is this is it. We have a quadratic lower bound. And there we are stuck. And we'll talk about these projects again later, about the projects of proving. But let me summarize what are the basic approaches to proving it. And we'll focus on one, of course. So the classical approach is the approach of just understanding how to prove lower bounds on simple circuits and just building up methods in order to eventually, more or less like Fermat's last theorem. In 300 years, we'll have enough tools. Geometric complexity theory, which was introduced about 20 years ago by Marmali and Sohoni, and you'll hear a talk from Ketan later in the week, is an approach to this problem that already brings the tools that we are going to talk a lot about here, the tools algebraic geometry, representation theory, invariant theory, and utilizing the symmetries that these two important polynomials possess. And the last one is the one I advocated before, is the connection of Cabanets and Impagliazzo through just developing an algorithm to this polynomial identity testing. So this is an algorithmic approach. And initially, it went through the tools of pseudo-randomness because it's a de-randomization problem. But now we are going to integrate into it invariant theory and optimization, and there will be several talks about this, of course. And the nice thing is that it connects very nicely with the geometric complexity theory approach. So I want to spend a couple of minutes on the polynomial identity testing problem just because it's so natural, even without this motivation of VP and VNP. And it will also motivate the word problem that we'll eventually solve, which is a non-commutative analog. So what's the polynomial identity testing problem? We already sort of saw it, but let me sort of restart. Polynomial identities occur all over mathematics. And this is, for example, the famous van der Monde identity. And you may wonder, how did he prove it? Well, of course, you know how he proved it. It's very easy to prove. It's a sort of an exercise. But in general, there are lots of identities that are only conjectural, and some that were proved, and it took many years to prove. How do you certify, even to yourself, that what you are going to, what you are going to spend years on is actually true? And that's the question. How do you verify an algebraic identity? And expanding, in this case, determinant is of course not the way, or evaluating in exponential in many places is not the way. And this general problem is I give you some implicit representation of a polynomial, or maybe a rational function, and I ask you whether it's zero. That's the problem of testing an algebraic identity. And it's really the worst problem for commutative algebra, whether two representations of an object like this are the same. The question, as I said before, has a very simple probabilistic algorithm. What is this probabilistic algorithm? Many people observed it over the years. You just plug random values to the variables you have and see what comes out. They just have to be sufficiently large integers relative to the degree. So, well, if the polynomial was identically zero, whatever you plug in will come out zero. If the polynomial is not identically zero, it's very easy to see that you will miss the variety with high probability. So it's a very, very simple probabilistic algorithm. You would believe that's really easy to de-randomize, but that's our problem. How to find a deterministic algorithm for this problem. And as I mentioned, again, Cabanet and Impagliazzo showed that it's not as easy as you think. It will imply this major separation between VP and VNP. So let's go back to, I should say that the proof here is not that difficult, despite the mystery in the statement, given the tools we have. Anyway, so we'll go back to the symbolic determinant, which is a problem that captures polynomial identity testing, and now I'll tell you about the problem we really will solve. Questions so far? Yeah.
Are there obvious cases where you expect the determinant to be much faster than polynomial? I mean, you have good candidates for where you expect the complexity to be high.
For the complexity of the permanent in general? The permanent in general, we believe, requires exponential time. That's
I understand it's well defined, but I mean, where the complexity of computing it is complicated. You have examples where you believe.
Yeah, just take a graph. You ask me which graph is it harder. Yeah, I am sure for you it will be natural to compute the permanent of the dimers in 3 dimensions. Okay. Yeah, so this is a very good example. But almost every example is good. Almost every. Just take any graph and ask for its permanent. The number of perfect matching in this graph. Yeah, the most graphs and most graphs that arise naturally, we don't know how to do it. Okay, so we are back to the slide I showed you before. This is the basic problem we have. We have a matrix of linear forms over a field, and we think of it as a symbolic matrix, and what we want to know, given these matrices, is L of x, is this matrix singular? So asking whether the determinant is identically zero is the same as asking whether this matrix is singular. Singular where? In the field of rational functions over these variables, right? So this is the problem we said we want to solve, but we cannot solve. That's the status of the problem. But this question has a dual life, and the dual life begins if you consider the same question with non-commutative variables. It's as natural as the first. What do we know about this? Well, first of all, what does it mean being singular when the variables do not commute? Well, there is a field, there is a skew field of rational functions over non-commutative variables. It's well defined. I'll talk about it later. It's much more complicated than the one you know, than the commutative one. But anyway, there is a field, and you are asking the same question. Can I invert this symbolic matrix over this field? Now, what is known about computation of this problem? It turns out that it was studied. It's very important in non-commutative algebra. And in fact, even decidability took a long time to prove. And it is highly non-trivial. And the best we knew is about 20 years ago is that this problem has an exponential time algorithm by Krohn and Rettenauer. And the main starting point of this whole project was the development of polynomial time algorithms for this problem. This is a paper with Gurvitz and Oliveira. This is an analytic algorithm for the problem. It works only over Q or C or fields of characteristic 0. And very soon, like a couple of months after, with developments that you'll see, Ivanius, Chiao, and Subramaniam developed an algebraic algorithm which works practically over every field, a very different one. Most of the talk I'll center on this result and this algorithm. So that's what I want to explain. Now, I want to explain what the algorithm is. Okay, so we are going to look at the non-commutative singularity. As you guessed from the first slide with all these problems, it is one of many problems we are going to solve. And let me start explaining the type of algorithm that we are going to use in order to solve this problem efficiently. Okay, questions? So the algorithm is going to follow what's called the alternate minimization heuristic. I'll explain it. And part of this sort of survey is the amazing power of this very simple heuristic. And in order to demonstrate it, I'll go again back to the toy problem that we are talking about, the perfect matching, and then we'll extend it to the symbolic matrix singularity. So I remind you of this slide. The perfect matching problem is this problem of determining whether a bipartite graph has a perfect matching. It has this expression, this way of looking at it, just whether the permanent of this matrix is positive or not. And I want to give you a very bizarre equivalent formulation of perfect matching. That the connection is not difficult. Basically, those who know the Birkhoff MacLane theorem about perfect matchings and permutation, doubly stochastic matrices and permutation matrices will realize it. But anyway, I'll make it explicit. And it's a problem that arose completely independently for completely different reasons. Maybe the first was Sinkhorn. There are even earlier papers, I believe. Here's the problem. I give you a non-negative matrix, like a matrix, like the adjacency matrix of a graph, A. Okay? And it is called doubly stochastic if the row sums are 1 and the column sums are 1. Okay? And scaling a matrix, so maybe A is not doubly stochastic, and you want to make it 1. That's what Sinkhorn wanted to do. You want to make it. And you want to make it using the following simple rules. You are allowed to multiply the rows and the columns by constants. That's all you are allowed to do. And you are supposed to make it doubly stochastic. So this is a problem again. You are allowed to, matrix form, you are allowed to multiply it on the left and on the right by diagonal matrices so that hopefully you'll make it doubly stochastic. And more precisely, the question is whether there exist such matrices, diagonal matrices, which can bring the row and column sums arbitrarily close to 1. It turns out that this is really the right question to ask, not whether you can make it exactly 1, but whether you can approach 1 as close as you want with such scaling factors. So that's a question. It's an algorithmic question. It's a structural question. Which matrices allow this to happen, which matrices don't? And it turns out that the answer is this connection I told you. Let's reverse the order here. This is possible exactly if the permanent of this matrix is positive. So it's just another way to represent the perfect matching problem. The permanent of this matrix is positive if and only if you can scale it so that it's arbitrarily close to doubly stochastic. And this connection will be the key to the algorithm. I want to say that the study of this problem had many reasons in numerical analysis, signal processing, approximating the permanent turns out. Leonid Gurvitz will tell you about connections to hyperbolic polynomials and this connection to perfect matching. But we are going to focus on this problem. How do we scale, or how do we check if a matrix can be scaled into a doubly stochastic matrix? So what is the problem? Let's look at a particular, maybe I should note that for later reference, that multiplying left and right by diagonal matrices is just chasing an orbit of this matrix under a group, that the group acting on it are these diagonal, these groups of diagonal matrices. So let's take a particular non-negative matrix like the adjacency matrix of this graph. We want to know whether it has a perfect matching. We want to know whether it can be scaled to a doubly stochastic matrix. So we want to make all the row sums 1. We want to make all the column sums 1. Right? And this looks hard because, on the face of it, there are 2n constraints. There are 2n degrees of freedom. It looks like a fair game. Of course, it cannot always be done. If the matrix was all zeros, then you cannot do it. So how do you do it? And here's an amazing idea, which seems absolutely naive towards this problem. You say, OK, I want all the row sums to be 1. I want all the columns to be 1. Let's take care of them one at a time. So let's try to treat the rows and columns separately and just fix them one at a time. So how do I scale the rows so the row sums are 1? Well, it's clear. I multiply the first row by 1/3, right? So this is the algorithm. What I'm describing to you, this naive thing, is the algorithm that will dominate the rest of or a lot of this conference, definitely these lectures. So let's scale the rows. We solved half the problem. We only have to scale the columns now. OK? Now let's scale the columns. Well, that's good. Now all the column sums are 1, but the row sums are not. So let's fix them. Here we are fixing them. Again, it's easy. And we scored the column sums. But you may be seeing where it's going. And it's not going anywhere good. That's where it will converge to. So it's not really converging. You can fix either the rows or the columns. So this algorithm gets into a loop, basically. And it doesn't converge, but that's actually not so bad, because this graph we started with and we wanted to find if it has a perfect matching does not. So that's maybe a good sign. We'll soon do another example and see what happens to the same algorithm with a graph that does have a perfect matching. But out of this algorithm, this greedy algorithm, is clear. What we do is just try to satisfy the constraints alternatingly. And that's why it's called alternate minimization. Let me maybe have a more formal way of representing it. If I add a bit of notation, if I just, for every matrix A, call R of A this diagonal matrix of the normalizing factors, and C of A similar for the columns, then I just iterate, multiplying on the left by L of A or by R of A, or on the right by L of A. And this is the whole algorithm. This is the alternate minimization algorithm. I should note that if any of the, I can freely take inverses here, because if some row is all zeros, then I know that it cannot be scaled. So this is it. And let's do it again on another matrix, which does have a positive permanent, does have a perfect matching, okay, corresponding to this graph. So again, let's scale the rows. Okay, all the row sums are 1. Let's scale the columns. Column sums are 1. Okay, the rows. I'm not sure if you see what happens, but things on the diagonal are increasing and things off the diagonal are decreasing. It's hard to see, but that's where it's going to. So this algorithm does converge, and this matrix does have a positive permanent. So at least on these two examples, what we wanted to happen happens. And let me spell out the algorithm again more formally. Let me, I mean, we don't have to, but for the analysis I'll talk about, because we are going to talk about the analysis of this algorithm. This will be key to what will come afterwards. Let's just think that the matrix was 0, 1. Okay, otherwise you have to take into account the length of the numbers in the matrix. So as I said, you repeat alternatingly scaling the rows and columns, and you do it something like n cubed times, polynomial number of times. It turns out that this number of times will suffice to know whether we converge or not. Because then, what we do is just test. Of course, when we stop, let's say the row sums are 1, we look at the column sums and see whether they are very close to 1 up to, let's say, 1 over n, in any norm you want. And it turns out that then we can declare that if they are close enough, we can say the permanent is positive. If they are not close enough, it will, it's 0, and it will never converge. And the main question, this is the same algorithm that Synchron developed, and over the years, many people analyze it in various ways. I want to explain the analysis that in a paper about 15 years ago, Lineal Samrodnitsky and I had for this thing that somehow magically connected to this project, and I guess inspired Leonid Gurvitz to what you'll see soon. So how do you analyze such an algorithm? It's obviously a sort of dynamical system. It produces a sequence of matrices. And the question is what you are trying to understand the limit of this sequence. And in any dynamical system, you want to understand convergence of what you hope you will have is some kind of Lyapunov function, some progress measure that you can use. And what we suggested in this paper is using actually the permanent itself of this sequence of matrices as a progress measure. So let's see there are 3 steps or 3 parts of any such analysis, and they will recur again and again to analyze convergence. And they are standard in any such dynamical thing. First of all, you want to put some cap, some upper bound on the value. And here it's easy. Why is the permanent always upper bounded by 1? Because either the rows or the column sums are at most 1, and the permanent is at most the product of the row sums, or the product of the column sums. So we always have this cap. Second step, you want to show that this progress measure increases at every step of your algorithm when you normalize rows or columns. And it turns out that if you are not too close already to 1, it will increase non-trivially. It will jump by a factor, by a multiplicative factor of 1 plus 1 over n. And again, this is extremely easy to establish. It's just the arithmetic mean, geometric mean inequality. So there's a second easy piece in this analysis. And the third piece is that the starting point is not too small. You want to say that if the permanent is positive, it's very easy to see that if the permanent is 0, you will get nowhere with this progress measure. If the permanent is positive, you want to say it's already sufficiently high. It's at least exponentially small in n. And then this multiplicative factor will bring it in polynomial time, very close to 1. And this third part, in this particular toy example, is easy. It's just one line of algebra. And this is what will become harder later. But this is a complete analysis of this algorithm, a polynomial time algorithm for perfect matching, which is different than the one taught in, in computer science classes. So it solves the perfect matching problem. It solves the matrix scaling problem. And I want to, so I have about 5 or 7 minutes to, I have more. The talks were planned for 75 minutes, but including questions, so I will stop soon. I want to, now that we have this template of the algorithm and its analysis for the toy problem of the permanent, I want to introduce the operator scaling problem, which is the one that will capture non-commutative singularity, and show you the analogy between them, and I'll start it again in the second lecture. Okay, so questions so far. This is the whole algorithm, that's the whole analysis. It's a really simple heuristic that just takes care of one piece at a time, works for this simple reason. Just you have to find the right progress measure. The first thing to say is that this progress measure is not the only one, and a follow-up paper of Gurvitz and Yanilos actually pointed out that there are other progress measures you can pick, and in particular they suggested something they call capacity, which will feature very strongly soon in the context of operator scaling. So this was a preamble to Gurvitz's work, which I'm going to describe now. So I want to talk about operator scaling. So I'm back to the problem in algebra we had. We had a tuple of matrices, right? This is the mother problem of perfect matching. That's what Edmonds defined. A tuple of matrices, they represent a symbolic matrix. And we want to know whether it's singular. As Edmonds defined it, he asked whether it's singular with commutative variables. And Gurvitz wanted to solve this problem. In order to solve this problem, he made what I consider a quantum leap, and this is also quantum leap literally, because he is moving to the quantum information theory domain. And he wanted an analog of the perfect matching problem that will bear the same analogy to perfect matching as the operator as matrix scaling. So he defined operator scaling. In order for this, we need to define a positive operator. So the analog of a positive matrix will be a positive operator. So in quantum information theory, a tuple of matrices describes a positive operator, a completely positive operator. It's a linear operator on matrices P. So L of P is just this formal sum AI, P, AI dagger. Okay, you can think of these matrices as complex. That's the usual way in quantum information theory. So we have this completely positive operator. It takes matrices to matrices. And in particular, it takes positive matrices to positive matrices. That's very easy to see, right? Positive definite matrices to positive definite matrices. It's important in quantum information theory because they deal with these matrices P represent quantum states. They are density operators, density matrices. Okay, so we have the analog to symbolic matrix. We now think of a completely positive operator. And the question is, what is the question we should ask? And he suggested this question: whether this operator is rank decreasing, whether the output of this operator ever has smaller rank than the input matrix. Okay? And that was a suggestion. This should remind some of you the whole condition from perfect matching. This is really an algebraic analog of the whole condition for perfect matching. Okay, so he guessed an analog, and he also, in continuing the analogy to matrix scaling, we have this operator, which is an analog for positive matrix. What is the analog for being doubly stochastic? And again, this is very natural. Oh, sorry, let me just say. Gurvitz proves that one direction, not if and only if. In fact, he realized it's not an if and only if. But in some cases it is. So there is a connection here. So it can help us solve the Edmonds problem. And for the algorithm, we need a notion of doubly stochastic. And there is a very natural notion. It's basically whether you apply your operator to the identity matrix, you get back the identity. So a positive operator is doubly stochastic is, in quantum information theory, is whether it's trace preserving and unital. So these are the analogs of being row stochastic and column stochastic. And so the question was, can you make such an operator, given an operator, can you make it doubly stochastic? And Gurwitz connected it to this problem. He showed an if and only if. Well, I guess here the if and only if, there should be equal here, then it will be an if, and it's the opposite. So there is this connection and suggests an algorithm, and maybe it will help us solve our problem. So this is a problem we are going to look at, the operator scaling problem. And what we realized 10 years later is that the right question that this is connected to is non-commutative singularity. We realized it because it was a result in the literature. It's a result of Paul Kohn from the 70s. So this problem, operator scaling, really captures the problem I promised you will solve, the non-commutative singularity problem. And the algorithm for it is the one. So the analogy is just pictorially between the operator scaling problem and the matrix scaling problem. The reason is sort of a natural quantum generalization I put here. It's the cartoon way of taking a classical problem and making it quantum is you take vectors to matrices, matrices to tensors, L1 to L2. And this is what is doing here. It's take a positive matrix to a positive operator, which is really a tensor, L1 to L2. The scaling conditions are really in L2 now. Doubly stochastic becomes this expression in the matrices. And what are we allowed to scale with changes, again. Vectors change to matrices. This means that diagonal matrices now change to non-singular matrices. So what we are allowed, or what we want to do when we are scaling an operator, is we are allowed to change bases on the left and on the right simultaneously to all the matrices. And using this sequence of operations, we are trying to make the operator doubly stochastic, or approach being doubly stochastic as close as we can. Okay, so that's the problem we are trying to solve. And I'll end this with the algorithm, and then I'll repeat it again in the beginning of the next lecture, is exactly the same algorithm as the algorithm for the matrix scaling. You just do the exact same things with these new definitions. Apply the alternate minimization heuristic. We are given a tuple of matrices. This replaces the matrix we had before. We want to scale it using invertible matrices so that, when I remind you, scaling it is achieving these, well, approximating these row and column stochastic conditions in this setting. And as before, like in matrix scaling, when we don't have row stochastic or column stochastic, we know exactly what to do. We divide by the right number, or in this case, by the right matrix. And here's what we divide with. If this doesn't happen to be the identity, then we divide every matrix by this R of L on the left, or by this on the right. So again, we can make an operator either row stochastic or column stochastic, but just one, very easily. And then the algorithm looks exactly the same. We are going to repeat a polynomial number of times the following operations. We scale the rows, multiply by this object. We scale the columns, multiply by this object, and run it for a polynomial number of times, and test whether we are close to being doubly stochastic after this number of operations. And as before, once we have done the polynomial number of times, we'll know whether it's going to converge or not. We can stop and say, if it is close, then this symbolic matrix is non-singular in the non-commutative case. We are talking only about the non-commutative case. And if it is not closed, then it will never become closed. It will never converge. And this matrix, symbolic matrix, is singular. I'll repeat this slide after the first lecture, and I'll tell you about the analysis. But basically, the analysis of this, I'll introduce capacity and so on. The analysis of this is going to be exactly the same. Only one of the steps in the analysis is going to turn out hard and therefore interesting, and therefore connecting to all the other areas that we talked about in the beginning. So let me stop here. Questions? Yeah? Yeah, it's take it to be 100 for now. Yeah, there is an explicit bound, but we didn't bother to optimize it. Definitely, yeah. Yes?
You mentioned permanents and determinants, but not immanents. Are they useless for?
They are not useless. They are studied a lot in mathematics, but I say they are not more interesting than the permanent. They are all hard. I mean, we believe they are all hard. As some of them are known to be. Some of them are known to be complete also for VNP, so they are as hard as permanent. And they are, they are just part of the VNP family, I would say. They are not, I don't know of additional thing they bring in, at least to my to my interest. In that. Maybe I need to learn more about that. Yeah, but at this point, in order to understand these two important complexity classes, all we need to understand is the permanent and the determinant. And they are as general as possible. If you understand the permanent, you understand the immanence, at least from a computational complexity perspective. Every immanent can be reduced by variance result, so that's a result. Every immanent, because all immanents are in VNP, every immanent can be translated into a permanent of not much larger size. If you bring me any n by n immanent, there's maybe n squared by n squared matrix of linear forms in the original variables, and the permanent of the latter is the immanent of the original. And this is true not just for immanents, it's for any polynomial you know. Yes, but that's more specific, yes. There's a lot of study of people study in algebra, so that's one thing that you mentioned. And also people study in commutative algebra, study, for example, determinantal representations of polynomials, analogous to like the same completeness result for VP. And they ask for more specific things. They want to represent a polynomial not just as a determinant, but as a determinant. If the original polynomial is a degree d, they want that the matrix will be d by d of linear forms. This is much harder. Variance result has this slack of polynomial size, okay? Or at least not a big slack, but it's... so there are specific conjectures that are more, that are not, answered by this connection. Yeah.
By the way, I will be talking about permanent conjecture.
Okay, so on Friday, Leonid will talk about this. Yes?
So it has to be Hermitian in the quantum analog, but it also has to be unitary, because I wonder if it is, then you can have a set of polymatrices and have an alternate quantum circuit question to the singularity circuit question.
You ask whether the matrix has AI have to be Hermitian? They are. No, they don't have to be Hermitian.
In the quantum case?
Yeah, they usually are, but I don't think they have to be for the definite. For the problem, you don't. They don't have to be. There's no reason. Everything works as is for any complex matrices.
You're asking about specific problem. Yes, for Pauli, yes.
Yeah.
It's an interesting question.
Yeah.
But here, no constraints, exactly like the other side.
Yeah, there's no more questions. Yes.
You meant historically interesting. You said, yeah, proof
well, the reference is maybe in the paper that in the original, but anyway, I can of course give the reference. He was looking at ordinary a system of ordinary differential equations, and the question is you want to eliminate variables. Basically, you want to it's n equations in n variables, and you want to eliminate somehow the variables. So you're looking for something like a perfect matching, but this really has the algorithm we know more or less. In which? I think in the paper that I think in the paper with Leonid and the original operator scaling problem, I think we have a reference, but if not, I'll get. There is a list, by the way, there is on the website of the workshop, there is a list of literature that's related to the workshop, and I'll add it to this also.
But it's not the Jacobian, it's like...
Well, there are several brothers, right? So Jacob.
They're related,
Yes,
yes?
yeah. So, but I don't know which of them.
It's probably son or nephew, because
It must be the son or the nephew of somebody, but
not that, but not that guy.
I don't know. I don't know. More questions? All right, great. So we have a coffee break for half an hour. So let me go again through this slide of operator scaling. So the plan for this this next hour is really how this project, became a snowball, basically, and diverged into lots of different directions. Part of the directions were required to just do the analysis of this algorithm, and then once we had the algorithm, it's like anybody in mathematics with a hammer starts looking for nails, and it's amazing how many nails there are there. So I'll talk about this algorithm and its analysis and connections. So repeating what I said before, let's have all the notation straight. We have a tuple of matrices. It can be, in this setting there, you should think of them as matrices over rationals, or let's say maybe rational or integer entries, or Gaussian integers, or so forth. And we are asking whether this set of matrices as an operator, as a positive map, can be scaled into a doubly stochastic operator. So what we are allowed to do is to multiply it on the left and on the right by invertible matrices, basically doing base changes.
But why would you be interested in doubly stochastic matrices actually?
Excuse me?
Why would you be interested in even scaling and getting to a doubly stochastic matrix? What is the
Into a doubly stochastic operator. Yeah, why would we be interested? Well, you asked Leonid. This is so he saw, as I say, maybe I should go back again to this. Yeah, why should we? Well, I'll tell you why he was interested. I said it, but I'll say it again. He was interested because he was hoping that in this analogy of matrix scaling, we already have an algorithm, right? We have an algorithm, we can apply it, and the question is whether the question we are asking has a bearing on the question that we want to solve, the Edmonds problem of singularity of symbolic matrices. And he showed one connection, and well, we realized that this was not the right connection. This connection is to a different problem, the non-commutative singularity, which happens to be as rich or maybe richer, even though I'm more interested in the first. Yeah, you may, yeah. So, yeah, I think you know probably better about your motive.
This doubly stochastic, my personal interest in doubly stochastic operators was because I was trying to prove analog of one-to-one conjecture for mixed discriminants, which is specific case of doubly stochastic operators, which when those matrices, it's a bunch of those matrices, but it's a specific bunch of rank one matrices. Okay. But that condition was not symmetric, so it was like the doubly stochasticity on one side roughly has n equations, another n squared. So I went to that thing, to that double stochastic. Okay. It's happened to be that I found an alternative proof for the van der Waals, but when I went to Los Alamos and I started to talk with people about this round one, I realized that it's connected to entanglement. That it's, and I started to, but anyways, it was lost somewhere between the motivation. But again, the original motivation was van der Waals conjecture for mixed discriminants.
I should add to what Leonid said that in this connection he realized that's one directional. In the case he was interested of rank 1, it's if and only if. So it's just that in general it's not here, and we are interested in the general case. So we are interested for many reasons. You will see how scaling arises in a completely different way later. But anyway, that's what we want to do. We want to scale an operator. We have this very natural algorithm to scale an operator. We just scale rows and columns separately, completely analogous to the way we do in the matrix scaling case, and test after a polynomial number of steps whether we are close. And this algorithm does the job. If we are close, then this symbolic matrix is non-singular, and if it doesn't, then it's singular. And what was the key to the analysis of this is a progress measure, just like before. I mentioned that we need a progress measure to analyze the sequence of operators that we are generating in this algorithm. And Gurwitz suggested capacity, which is a quantum generalization of the capacity he and Yanilos introduced for the, as I mentioned before, analogous to the matrix scaling one. And it's a very natural definition. Take a look at it. So what is the capacity of an operator? You compare the determinant of the output to the determinant of the input, and you take the minimum or the infimum over all positive definite matrices. Okay? It's natural, but it's certainly not convex, and it's maybe hard to understand, but it is the right measure in the following sense. If you apply the same 3 steps of analysis that we talked about, they work in the same way. So first of all, he proved that, well, he proved, and we should add here, he proved it for his rank decreasing condition, and we said it's equivalent by Korn's result to non-commutative singularity, that yes corresponds to positive capacity and no corresponds to 0 capacity. Just we had positive permanent and 0 permanent. The analysis has 3 steps as before. Capacity is at most 1 for all these operators. If they are either or column stochastic, it's easy. Progress is the same proof as before. It's just exactly AM/GM, very easy. So what remains? What remains is to lower bound the capacity, given that it's positive. You want to say it's at least some exponential factor in the size of the matrix, and then in polynomial time number of steps you will converge, right? Because you are jumping by these steps. And this, he couldn't do. And this is what eventually we did in the joint work with him and Garg and Oliveira, and now I'm going to explain where it is coming from. Okay, so why this becomes hard, and what do you need in order to establish something that in the matrix scaling case was a one-line piece of algebra. Okay. I'm just mentioning this algorithm not just tests non-commutative singularity, it in fact computes or approximates arbitrarily well the capacity function. And because this is non-convex, this just aids, and I'm starting with the connection to optimization in this part of the talk. This adds to the arsenal of tools we have to battle, non-convex problems that we need to in optimization. And we'll explore some of these potential applications. So just reminding you that because non-commutative singularity is in fact equivalent to all these problems I mentioned in the beginning. This polynomial time algorithm that we now got is a polynomial time algorithm for all of them. And for some of them, I think it's really interesting that we have it, and other connections between them are sort of useful as well. But going back to the analysis, I want to say where in fact, I'm describing it more or less chronologically because our understanding of what we actually did evolved with time, and you'll see how it evolved. And this is how we understood it then. We understood capacity as very basic, and in fact, here's what specifically about capacity made the connection between the three different areas that I want to talk about. So you should think of having not one operator, but two operators. So one A1 through AM and another D1 through Dn. Okay, maybe one is n by n and the matrices are n by n, the other is d by d. And what we are going to look at is this expression. This expression will turn out to appear in three different places. It's the determinant of the sum of the tensor product of these matrices AI and DI. Okay, this is going to be key to the analysis. So where does it appear? It appears, first of all, this is part of the analysis which I will not show you, but I'm just telling you it's an important part. It turns out that it's useful in order to analyze the algorithm to study the capacity of the tensor product of two operators. It's a very natural thing in quantum information theory, the tensor product of two positive maps. And there's a very simple inequality, one line you can prove, which is key to the analysis. But in this expression, you find this determinant. So where else do you find it? And I'll elaborate on the second two in a second. You find it in non-commutative algebra. It turns out that testing, again, I'll explain it in more detail, testing whether some rational expression is a zero element in this weird field of rational functions of non-commutative variables is the same as testing whether the determinant of such an expression is zero for all possible choices of plugging DIs of all sizes. So, again, I'll elaborate, but it appears there. It appears there as a fundamental theorem. And that's important to us. And it also appears in invariant theory, which, again, I'll elaborate on. It appears when we are looking at the set of invariant generators for the invariant polynomials under a certain group action on a tuple of matrices, where we think of the entries of these matrices as variables. If we look at the invariant ring, which I'll define soon, we find exactly this expression. And the fact that this expression appears in all of them is what, made everything tick for us then. So let me talk about these two areas and just explain a bit more how they appear there, these expressions. So first, non-commutative algebra, it's all going to be very brief, and there'll be talks that will elaborate on this, of course. Order is important in mathematics. Non-commutative variables is what we are going to deal with. So I want to explain what is this free skew field. So you have a bunch of non-commutative variables over a field, and non-commutative polynomials are a simple enough objects. You just write, just monomials, you have to remember that the order of variables matter. So you have more monomials. But that's simple enough algebra. Now you want to close it, you want to localize it like you do in the commutative case to get a field. So you do it. How do you do it? Well, it's not so simple, and that's a body of work that's very substantial. The easiest way is to just close it under the operation of inverse. Just allow addition, multiplication, and inverse. And then you get rational expressions. And that's, in fact, a very good way of doing it. The question is making sense or having canonical form. In the commutative case, canonical form is the ratio of two polynomials. This is far from being the case. Even this simple expression is not. is not a ratio of polynomials in the non-commutative case. You can check it, it's fun. And then you get into more elaborate things. You can have nested inversion. This nested inversion cannot be unnested. And there's a fundamental theorem of Rethenauer showing that nested inversion can be arbitrarily high without simplification. So the objects here are far, far more complex than in the commutative case. On the other hand, sometimes you can simplify. So for example, this is a famous Suarez identity. It's a fundamental theorem of projective geometry. And it's a statement that these two rational expressions are identical. You see here there is a double inversion, and here there isn't. So sometimes you can. So when can you? And this is the basic word problem of non-commutative algebra. I give you a rational expression. Is it identically zero? This is one of the problems we'll solve. So what are the connections that, where does this expression comes up? There are two fundamental theorems in this area that I want to mention that bring up the connection to this capacity. One is the theorem of Amitzur. So how do you know if a rational expression is zero? Well, one way is more or less the definition. It's not yet the theorem. One way is just to say, well, plug everything you can into these variables and see if you get a zero, right? What is something? Well, now it's not scalars in the field, it's non-commutative, so plug in matrices of all sizes. So this is more or less the definition. This is zero if and only if everything you plug in and is defined is zero. What Amitzur proved, that a much stronger result is this. That you don't have to look at this large matrix to see whether it's all zero. It's sufficient to check whether it's non-singular. The determinant, which is just one number, tells you whether this expression is zero. So this rigidity theorem will become very important in K.V. Subramaniam talk and Visu Markham talk and other talks later. This is a basic theorem in non-commutative algebra that's very important. Now, how does this connect to capacity? Through another result of Kohn, which is a canonical form for rational expressions. So I mentioned that it exists, and here it is. Every rational expression can be encoded by a tuple of matrices. I'm not going to explain to you how, but every rational expression can be converted to a tuple of matrices. The size of the matrices and the number is about the size of the expression itself. And it is done in such a way that the rational expression is identically zero, what we want to test, if and only if this expression, this symbolic matrix, is singular over the skew field. And for those of you staring at it, it should remind you, what should it remind you of? Which theorem which you saw? I showed you a very similar theorem in the commutative case. Valiant's theorem. The symbolic determinant captures commutative formulas is the commutative analog of this theorem. Now, this theorem is stronger, happens to be stronger. It includes division, and it is non-commutative. It was also proven earlier, but of course in a different universe. Anyway, so we have this connection between rational expressions and symbolic matrices here, and now we can plug Amitzur's result to this, and what we get is that an expression is zero exactly when this determinant is is zero for all choices of matrices di of all sizes. So it appears here. So we already see the appearance of this in non-commutative algebra with this rigidity theorem, and this is basically what we want to test. We want to test whether an expression is zero. That's one of the formulations of the problem we want to solve. And clearly, this is an infinite number of equations. How do we do this? Well, for starters, it makes sense that we try to bound the degree of the. Do we need really to consider all sides of matrices? Maybe we can just look at matrices up to a finite size. Maybe we don't need to look at all of them. So where are we going to get such a result? And this result is going to come up from invariant theory. So again, we'll have several talks about this. Invariant theory, the afternoon will start with the study of symmetries, group actions, orbits, and invariants. There are many examples: graph isomorphism, the action of symmetric group on the vertices, billiards, the action of just, here the group is time. You just send the white ball and see what happens. This group is very interesting. Just you cut these shapes and move them about in the plane. And this is a group. And in all these group actions on these objects, we want to understand what doesn't change when you apply this operation. What are the invariants of these processes? And well, in this case, it's well known that the area is preserved, and in fact, the only invariant. Here it's a physics story. The invariants are momentum and energy. Here we don't really know, and so on. So I want to talk about a particular side of invariant theory, and Harm Dirksen will elaborate on this a lot in his talk. We are going to talk about linear groups acting on vector spaces, and therefore on polynomials in this number of variables. And the invariants we are going to look at are the polynomials that remain invariant under this action. So we are going to do a linear change of variables using a group element, just a linear change of variables. This takes a polynomial to another polynomial. If it stays the same, if the polynomial resulting stays the same, it's an invariant polynomial, and this is the ring of invariant polynomials. Now, you know many of examples of this. For example, if G is a symmetric group, it just permutes the variables, then the invariant polynomials are the symmetric polynomials. That's why they are called symmetric, and they are generated by the elementary symmetric polynomials. So we already know that in this case, if we are looking at Sn, you just need to look at degree n generators. Another example, you know, suppose we take a matrix and we act on it by changing bases on the left and on the right. So the variables of the matrix are permuted by this change. Then the only invariant polynomial under this action is the determinant. So all invariant polynomials are generated by the determinant. So these are things are well familiar, just put in the language of invariant theory. And it turns out that what we are interested in is a generalization of the second example, right? We are acting on a set of matrices of variables by changing bases on the left and on the right. Okay? And the question is, what are the invariant polynomials here? And this is an object of study of invariant theory. So I've just repeated it here. And lo and behold, around the year 2000, several groups of people, Domukos and Zubkov, Dirksen, Weyman, Schofield and Vanderberg, characterized generators for this invariant ring. And it is the same expression. You just take all possible determinants of this form with all possible matrices. So it's the same object. And it appears naturally there as it appeared before. And in invariant theory, there is a tradition, and it's important to study how small the degrees of the generators you can take. So in particular, if you want to solve the most basic question in invariant theory, just ask the null-con question, just ask whether for a given tuple, does it vanish on all invariant polynomials, then, well, if you had a bound on all invariant degrees, you can try them all, for example, if you had a few generators. So what is the bound? Is there a bound? And this goes back to, okay, I'm just mentioning it. This turns out to be exactly equivalent to whether the capacity is 0 or not. And this history of degree bounds go back to Hilbert, who first of all proved that there is a finite bound. There's always a finite bound for this class of group action that Dirksen will elaborate on. And then people started looking for bounds, and the first explicit one, I guess, was Popov. And then this bound that Dirksen proved about 15 years ago was, when we realized it, was the key to get the bound, the exponential lower bound on the capacity. And this led to this analytic paper. And a couple of months later, Dirksen and Markham improved their bound on the degree here to polynomial. And this allowed the algebraic algorithm I mentioned of Ivanya's, Karen Subramaniam, that you'll hear about also, algebraic or combinatorial algorithm that will be discussed later. And I want to say that the degree bounds were not only important for this problem, so this gave the polynomial time algorithm for this problem, but also, as you will see later, for the isomorphism problem, which is a more general problem, where you want to know, well, it's usually called the orbit closure intersection problem, where you want to know whether two tuples are isomorphic, whether they have the same values on all invariant polynomials. This is a really very important problem of geometric invariant theory, and it will be discussed in several lectures. So we have an algorithm for this problem, and now we are questions so far. Yeah. Yeah.
So I think it should be stressed that for that paper 15,
yes.
actually Hilbert was sufficient.
Yes, that's a good point, which I considered skipping anyway, because we understood later with a finer analysis, and it's in the final version of the paper, that this analysis, the polynomial time analysis for this paper, actually can make do with Hilbert. However, the reason I'm sort of skipping it, that's okay, it's a good comment, is that for all the later algorithms, which I'm just going to show you now, we do need such bounds. We do need such bounds. So, okay, so let me tell you about now this snowball. More questions. So I'm going to put it in a general framework, as we did in these papers, as alternate minimization algorithms where the objects are groups, where the objects, where the parameters are group elements. So let me do it. So here's how it looks. This is more or less what we had before, and I'll just generalize it. This is just the hammer and nail story. We had matrix scaling in which we acted on a matrix using two diagonal groups on the left and on the right. This is the operator scaling when we acted on a tensor by left and right basis change, SLN actions. And the algorithm was this alternate minimization. We did right, left in both cases. And the analysis was using this potential function on the permanent or capacity, and that's how it works. So I want to stress that we started with a goal of scaling. In both cases, the goal was scaling, and the algorithm needed, in order to be analyzed, needed some potential function. What I want to show you now is an understanding when we look at it in this way, and we use the tools of geometric invariant theory, that actually scaling, despite the fact that it has many reasons to be studied, as I mentioned before, arises naturally even if it has no reasons at all. Scaling is a very natural thing to do. So let me explain how, and there'll be an elaboration in the two talks tomorrow morning. So let's start from a goal, from an optimization. So now we are into optimization. Suppose we are in the same setting. We have a product of groups. So let's say you can think of them of all CLNs, SLNs. So a product of groups, maybe k of them, not two, acting on a tensor. Okay, and the way they act is the ith group acts on the ith fiber of this tensor. Okay, and we are given one tensor, and we ask, what is the smallest norm we can get it to be under this action? We just try to minimize its L2 norm. It's a basic optimization question. You can ask why, I'll tell you in a second. So, but it should be clear what is the task. You're just given a tensor and you are trying to find out the smallest L2 norm you can get it to be under the action of this group. Okay? So we start with this goal, with the optimization goal. And find the lightest vector in the orbit of this group. Okay? Why? Well, we saw in the case k equal 2, it's really matrix scaling and operator scaling, depends what groups you use. Turns out that in the case k equals 3, it comes to a basic question representation theory, asymptotic Kronecker coefficients, and for large K, it comes to the entanglement distillation problem, that's a problem in quantum information theory. But basically, the reason that it's interesting in geometric invariant theory is that this minimum, this infimum is 0 exactly when this tensor is in the null cone of the action. Namely, you can drive the norm of it to 0. 0 is in the, you can drive the whole tuple of the whole tensor to the 0 tensor using the group action. And that's a basic question, and it, of course, is a generalization of the question we were studying before. That was one of its incarnations, the null cone problem. So that's the reason to study this goal. So what does it have to do with scaling? It looks like a very different thing that we are trying to optimize. There's no capacity here. And here is the connection. This connection is duality. So we said this infimum is 0 if we can drive the vector, this argmin of this infimum is the zero tensor. So this is a situation when you can make it a 0. You can ask, what if it's not 0? What if this infimum is not 0? You're asking a duality question. So you have a necessary condition. It's 0 if you can push it to 0 using group elements. If it's not 0, what is a sufficient condition? Can you prove is a duality theorem? And here's a very basic duality theorem that Ankit Garg will elaborate on. The Kemp-Ness theorem. There is a characterization. It's positive, this infimum is positive exactly if this infimum is doubly stochastic. I didn't define doubly stochastic. You have to define doubly stochastic, and he will define it. And in fact, it should be really k-way stochastic because there are k parts. But scaling, this is a scaling condition. You can, so just like happened in operator scaling, it's positive, it's scalable to doubly stochastic if and only if capacity is positive. The same is here with this minimum norm condition. So there is really an if and only if condition that has to do with scaling. Scaling arises completely naturally in this context if you consider this optimization problem, even if you didn't care about scaling at all. This is simply the condition for not being in the null cone. And it turns out that the minimum of the L2 norm and the capacity that Gurwitz defined have a very intimate connection, despite they don't look alike. And looking at both of them together have very important and complementary advantages. So I want to say something about what comes into the, so we have this duality, we have an algorithm, a natural, yes?
So is there an analog of NC-RAND here?
No. Not that there are, so you can ask, is there an analog of the whole condition? There is an analog, but it's not so nice as in the, and it manifests itself in really interesting ways, but let me not get into this. Yeah. But it does tell you, for example, that this being in an null cone or not depends, for example, just on the support of the tensor, which is really interesting. Yeah.
Why do you call this non-commutative reality?
Why do I call what?
Why do you call this non-commutative reality? I don't see any non-commutativeness in the statement.
Non-commutative, where did I say not? Why do I call it? Ankit will explain why it's non-commutative. Because it's over groups. It's a generalization of the linear programming duality you are familiar with. And that you'll see why it's non-commutative. It's not the same non-commutative. It's a different non-commutative. Thanks. Okay, so the upshot of just doing the same thing as Gurwitz did to matrix scaling, and we are now doing to the operator scaling, just running alternate minimization, it's very easy to see that locally you can improve on every coordinate. You can scale every coordinate separately and just run through them, let's say in a cycle, make them scale the first, scale the second, and just iterate it and run it a polynomial number of times. Works. It works. It will converge. You will converge to doubly stochastic, if at all possible, in a polynomial number of times, a polynomial number of steps. And this is big. Why is it big? Because of the problems this is capturing. How do you analyze it? Well, you analyze it in the same way. You just have this three-step analysis. And as before, the key thing is proving this lower bound. All the others are easy. And this work, well, I'll just flash something. You'll see it in a lot of detail. The way it works is basically, that's what we need to prove. We need to prove a lower bound on this value of the progress measure. And you basically look at your invariant theory, and you have to prove things. And I just want to put the contrast in what happened, I would say, traditionally, maybe for a century in invariant theory for problems like null-con, and what is happening now with this algorithm that's completely sort of out of the box for invariant theory. It's analytic. So a tensor, let's say, is in the null-con if it vanishes on all invariant polynomials, and I want to stress it vanishes on all. So testing all of them leads typically to doubly exponential. I didn't write it here, but I wanted doubly exponential algorithm. What we are going to do is instead continue with the same spirit, bounding the degrees of generating polynomials, and it turns out bounding also the height, the coefficient size of invariant polynomials. And I'm mentioning Cayley here because maybe his paper of 1846 was the big breakthrough of the generation of invariant theory. And in it, he has already a beautiful algorithm called the omega process. Invariant theory is a very algorithmic subject. And
just one comment. I mean, you write must prove, psi, b, positive, you write blah, blah, blah. But I think you also assume that this, now it's a tensor, let's say it has integer coordinates.
no, this is 0, 1. Otherwise, you have to, as I said before, yeah, it's a very good comment.
Otherwise, it will not be true. I mean, there is some, it must be somehow discrete.
If you see this, you should think of n as the input size, really the input size in binary, not just the size of, yeah, thanks.
The same true in the
In all of them, yeah, also in the operator scale. So I just wanted to mention that in order to prove the new bounds we need, there are tools that are extremely classical, go 150 years back, and provide us with this ability to prove bounds. And of course, there are other methods, and you'll hear about them in the talk. But now in this algorithm that is solving this general problem of tensor scaling, to test scaling, to test this, we just need to know that there is a polynomial that doesn't vanish. We don't need to run through them. The analysis just uses the existence of this polynomial, and using this existence, I'm not going to explain it, but using just this existence, we can, and the bounds on degree and height, we can relate, we can prove a lower bound on the expression, on this expression, given that it's non-zero. That's where it's coming from, and it will be explained in detail.
But it's kind of similar when you use permanent.
It's very similar. It's almost
it's not exist. It's existence, but it's not existence. Yes?
No, but you have to know.
You cannot compute permanent.
That you cannot. Yeah, I take. You are right. So there the reason is computational. Anyway, it seems that here it's worse than permanent because most known algorithms are doubly exponential. At least in the permanent case, we could do it in exponential. Yeah, so that's what I want. So I'm continuing on the theme and variations to show you where it continues going. We talked until now about scaling to uniform marginals, to doubly stochastic matrices, doubly stochastic operators, doubly stochastic tensors. But in fact, you can ask, and people did ask, what about scaling to some other marginals? And even for matrix scaling, people looked at it 50 years ago. You want to scale a matrix, a positive non-negative matrix, to having marginals that are just prescribed, some vectors, P and Q. Okay, you want row sums and column sums to be something else than all one. This is a basic problem. In operator scaling, it's again very natural. You give marginals. You don't want it to be the identity. You want it to be some matrices, P and Q. Well, again, why should you look at this? Well, let me mention, of course, for tensor scaling, and Michael Walter will talk a lot about this. Here are some examples where it comes up, exactly these non-uniform marginals. A classic problem in algebra, the Horn problem, I give you a bunch of real vectors, lambda I, think of them as spectra, and here's the question. Are there Hermitian matrices with these spectra, these real spectra, whose sum is 0? This led to a lot of, this is a big subject and beautiful subject, and you'll hear more about it. But it's a special case of non-uniform marginals. Here's another one, the quantum marginal problem. Just like the classical marginal problem gives you a set of marginals for a probability distribution and asks whether there is a distribution that has these marginals, in quantum information theory you can ask, is there a quantum state, a k-partite state, which has given marginals? This is a special case, which we also, this algorithm works for. And I mentioned Kronecker coefficients. So all of these now come under the, we have an algorithm for this problem, and you'll hear more about this again, later. So this is non-uniform scaling. And all the algorithms are the same. It's the same alternate minimization. Sometimes the analysis is more sophisticated, and well, you'll hear more about it. I just want to mention, as we are going to enter more into optimization applications, that moment polytopes arise. Somehow in this group action on tensors, or in general on varieties, it turns out that polytopes, the objects of linear programming, arise, and they are important. They actually capture the problems mentioned here. And having an algorithm for this, really having some kind of weak membership oracle for this type of polytopes is at least a hope that we will be able to use these techniques for applications in optimization that are more classical. But anyway, this is a very important thing I want to mention. And the last thing I want to mention in this sequence of generalizations is that actually we ran out of steam in some sense. Yes, question?
So is there a natural, Kepnes type of argument for this non-uniform argument?
Yes. And yeah, it will be discussed somewhat, yeah. In fact, there is a reduction. We have a reduction. One of the ways to solve this is reducing the non-uniform case to the uniform case, and then you can use the Kepnes theory. The other is generating appropriate capacity functions that tailor to the marginals you want to achieve. Yes? So alternate minimization, just has this limitation. It's this limitation. If you want to convert to scaling up to epsilon, the running time is polynomial in 1 over epsilon. This is great in polynomial, but it's not so great, because in some applications, what we really need is exponential convergence. We need what's so-called strong membership. Anyway, you need faster convergence. For example, well, I'll mention it. So what do we do? And it turns out that this, again, opened for us a new direction of study, and for others, not just for us, new direction of study, bringing back other methods of convex and non-convex optimization to the same kind of problems. Maybe you can use them to get better convergence for the same type, so forget alternate minimization. This was done already long ago for the matrix scaling problem, because there it's really a convex, it can be convexified, and there you can use classical gradient methods and get them to converge exponentially fast. So this was known. But for operator scaling and tensor scaling, it's not convex and it's hard. So what do you do? So in one work that we did, which was needed for orbit closure intersection, we did it via geodesic convexity. So it turns out that while capacity is not convex in the usual metric of Euclidean geometry, if you move to the hyperbolic metric over positive definite matrices, then it becomes convex. And then you can try to use some of the methods. People studied geodesic convexity. They studied mainly first order, and in order to get exponential convergence, you need second order. So we developed some, and we did it this way. It turns out this particular thing can be done algebraically also, and you'll hear about that. And it turns out that this, move of this type of problems into just general convex and non-convex optimization had an amazing consequence that you, again, will hear about from Lapchi-Lau on the Paulson problem. It turns out that you can use smooth analysis and variance on these algorithms, and you solve a classical problem in operator theory that was open for a long time. Purely mathematical question, but it goes through this algorithm and these various analyses. Before I talk about the last connection of application to analysis and optimization, I want to go just back for a second to alternate minimization, because I feel that this, shining the light of group theory on alternate minimization is valuable. And there are lots of problems in optimization where alternate minimization is just used as a heuristic, and it cannot be analyzed well. And often, at least as we discovered, groups are there even if you don't see them. Like in matrix scaling, it was not totally clear that there is an orbit that you should look at. So let me mention just, for those of you who haven't seen alternate minimization in this context, just by giving you a few examples, and then I'll move to the last part. So alternate minimization in general, so we've seen it in the group setting, but in general, it's this type of problem. It arises it has applications in statistics, optimization, machine learning. You just have a multi-parameter objective function, f, of maybe k parameters, and you want to solve it. Maybe you want to minimize or maximize it, but you will see you may want to sample from something, or solve can mean various things. And it's complex, but solving it for any one coordinate is easy. If you fix all the others but one, then solving is easy. And then, okay, what do? You just iterate like we saw before. And this is used all over the place, as I said. And here are some examples we don't understand so well. One of the earliest examples is this of von Neumann. It's actually a convex problem, but it turns out to be more efficient to do it the way he did it. I give you two convex sets, okay? And you just want to, somehow they are given, and you want to find the minimum distance between them. So how do you do that? Well, here's a very easy alternate minimization. You alternately project. You start arbitrarily at some point, right? And then you just find the closest point in the other body. That's a convex problem that's easy. And then you find the closest. Then you find the... Oops. So this converges, but we don't really know criteria in general. We know we have pretty good understanding of this but not complete. So that's a simple example. Another example, which is more complex and is open, is Nash equilibrium. There's a two-player game. I'm sure you know it. So there are two pair of matrices to two players, and what they are looking for is a stable strategies, stable probabilistic strategies. What does it mean? It means that given the strategy of one, you cannot do better than what this pair is offering you. So it's stable. This pair of strategies is stable. You cannot beat it with a different one. This is a non-convex problem. We don't know how to solve it. It's a very important problem in game theory. And one natural dynamics for it is the way probably it happens in real life is, you look what the other, people adapt their strategies and you do best response to the previous, and you generate just a best response to the previous, to your opponent's game. And this is easy to compute because it's a linear program. But this doesn't always converge, and if it converges, sometimes it's exponential time. We don't understand it well, but that's another example. And the third example I want to show you is just very different. It's a sampling problem. You probably have seen it, but you never thought of it as alternate minimization. This is Gibbs sampling. You have a complex probability distribution to sample from, and it's hard to do it at once. So you just do what you can do conditionally on one coordinate, one at a time. So here's a famous example. How do you generate a random legal coloring of a graph? Let's say you have a 3 regular graph here and you want a random 4 coloring. Well, you can start from an arbitrary coloring and then just move one vertex at a time and replace it by a random legal color. So here's the random legal color here, the random legal. But how many? It converges to a uniform on all legal coloring, but how long does it take? We don't know. So that's another example. Anyway, this was just to entertain you with lots of potential places in alternate minimization where maybe group theory and invariant theory will help. Questions so far? Because that's my last topic, the last 10 minutes. All right. So this was maybe the most surprising connection of the operator scaling kind of works, because as I explained at the beginning, the motivation was algebraic. It still is algebraic. It's about understanding singularity of symbolic matrices. And it turns out that sort of magically it's related to analysis, and I want to explain this connection. And because of this connection, there's even more, at least potential for applications in optimization, and I want to explain this connection. And this connection is through the so-called Braskamp-Leib inequalities, which I'll now define. So Braskamp-Leib inequalities, here's the resume. It's, so many inequalities are special cases of Braskamp-Leib that they appear all over the place. Cauchy-Schwarz and Helder and Loomis-Whitney and convolution inequalities and hypercontractive inequalities and Brun-Minkowski is a special case, and lots of inequalities, fall into this framework. So it's sort of an amazing framework for at least claiming inequalities and then seeing whether there is one. So let me say how it looks like, this framework. So first, the Helder inequality, of which is a special case, is this one. We have the integral of this product, right? And it's bounded by the product of the norms for any two norms that add to 1. So I'm using here 1 over pi for a reason. And I added this constant 1 here because it's important. Of course, it's true for Helder. So what's the general formulation? The general formulation is this. So it's a vast generalization. What you start with is a bunch of linear maps from Rn to some smaller spaces, and a bunch of non-negative reals. And what you ask whether the integral of the product, and the product here you apply a function to a projection of your vector, is bounded by the product of the norms with some finite constancy. So this is called the Braskamp-Lieb data. For any data, such an inequality is true or false, exists or not. And that's exactly what we want to know. This is exactly, all these are special cases because somebody proved such a bound. So what we ask whether there's a finite constant C, so that no matter what functions you plug in here, you get an inequality. The inequality is valid for, let's say, integrable non-negative functions. Okay, these are Braskamp-Lieb inequalities. So what do they have to do with this? We'll see in a second what they have to do with this. But the basic question is, when is such an inequality valid? So you would like to know, feasibility. Is there a finite C? You would like to know optimality. If there is a finite one, what is the best one? What is the best constant? And you want to know other things like continuity and so on. So in some sense, you remember I talked about proving how do we certify algebraic identities. That's an algorithmic question. I give you here it's the same type of question. I give you a candidate inequality. How do you certify it? How do you test? And this is what we can do also in polynomial time because of the same algorithm. And I want to explain where is it coming from. What is the connection between this analytic question and the operator scaling result? So it's clear. And of course, I'll ask also whether there are applications to this. Okay, so let me explain. And this is, the connection comes from a basic result of Elliott-Lieb, which characterizes the optimal constant. The characterization is somewhat implicit, as you'll see, but it's valuable enough to see immediately the connection to operator scaling. Okay, so here is again is the general Braskamp-Lieb inequality. Here's the data, and here's the formula of the inequality. And you want to know what is the optimal constant. And remember, this has to hold for all possible functions. All possible functions. And what Lieb does is tell you which functions make it optimal. He tells you that this is always optimized in Gaussians. In some Gaussians, with some correlation matrices, but always Gaussians. And those of you who will come to James Lee's talk will be related to this, and also Nishit Vishnoi's talk will be related to the how this is proved. I'm not going to talk anything about the proof, but once you know it's Gaussians, you can plug the formula for the integral of a Gaussian. And this is what you get, that the optimal constant is this expression. You just have to find the maximum. The maximum constant is the maximum over all positive definite matrices that you plug into this expression. Don't try to understand this expression. But if you just stare at this expression, what does it remind you? Capacity. It looks like capacity. It's just slightly more complicated. And indeed, that's how we solve this problem. This expression is the capacity. It's a non-convex, it's obvious. This is the capacity of some operator. The solution to the feasibility and optimality problem for the Braskamp-Lieb inequalities is a simple reduction. You just take the data, take these matrices and these vectors, and you construct an operator, and whether it's scalable or not, it tells you what is whether it's feasible or not, and the optimal capacity which you can compute tells you the optimal constant. And so there's a simple way to construct it, and I'm not going to show it to you. And with hindsight, for those of you who know quiver representations, and maybe Harm Dirksen will tell you a little about this, this is a reduction. This reduction is, in fact, a reduction known in invariant theory between two quivers, this, I guess, star quiver and parallel quiver. But anyway, that's for experts. Now, where is the optimization connection? Why is it useful? So far, questions about this? So again, The connection here is, again, because of this unity of mathematics and things arising in the same way in completely different and disjoint areas of mathematics. This expression that arises here is simply the capacity of an operator, and we know how to compute it. So what is the connection to optimization? There is a beautiful paper of Bennett, Carberry, Christen, Tao, which discusses the feasibility of Braskamp-Leib inequalities in polyhedral terms. So they just ask whether there is a finite constant that makes such an inequality hold, given the data, the B's and the P's. And here's their kind of characterization. So again, this is the same picture. That's what we are after, to know whether there is a finite C here. And they tell you that this happens exactly if the vector of P's, this vector, sits in a polytope defined by these matrices somehow. And somehow is this way. So again, C is finite, there is an inequality if and only if P is in some polytope defined by the linear maps. And this polytope is really, really simple. Here are the inequalities and the equalities defining it. There is some normalizing condition about the maps. These maps go from Rn to Rnj, so some normalizing condition. And then you have an inequality for every subspace of real space. Okay? For every subspace, you want this, weighted sum of dimensions of the projection of the subspace to have this inequality. In fact, it's an infinite subset, it's an infinite number of inequalities. And the last one is the PIs are known. So this is a linear program. This is a linear program that completely captures the feasibility of Braskamp-Leib inequalities. Now, I said infinite number of conditions, but of course, all these weights here are just integers between 1 and n. Right? So they are just exponentially many. They are exponential, so there are linear programs with exponential number of inequalities, which we can test in polynomial time. This is a great thing to do if we just had natural polytopes that manifest themselves as Braskamp-Leib inequalities. And I'll show you in a minute some. I just want to point out that if you look at this again, you will see, and the reduction I mentioned in the previous slide makes it explicit, you will see that these conditions are exactly translate to the rank non-decreasing conditions that Gurwitz had for operator scaling. So when you translate this problem into an operator scaling problem, these conditions translate to the exponentially many non-decreasing rank conditions. So there's a complete analogy. This is just a special case, as it turns out to happen. This is a special case of operator scaling. So let me just conclude with a couple of examples of polytopes we know are Braskamp-Leib polytopes. Unfortunately, we also knew how to solve them before. So, and I should mention, these are also moment polytopes. So applications, what large linear programs manifest themselves as Braskamp-Leib polytopes? Matroids, so that's a very simple type of polytope. A matroid is just a representable matroid is just a bunch of vectors in real space. That's n-dimensional vectors, m n-dimensional vectors. They define a polytope in a natural way. I'll just use this notation, just a set of all vectors indexed by a set. And the polytope associated with this matrix is just a convex hull of all tuples of all bases, right? So if you find n independent ones in here, they are a vertex in this polytope. And you take the convex hull of all these vectors. That's a matroid, that's a polytope of this matroid. And people understand very well, and it's simple to understand what are the facets of this polytope. These are the facets. I mean, I'm not going to read them. They are very simple. But the point is, and it's just an observation, that if you define just rank 1 operators in the Braskamp-Leib setting, you get that this polytope is in fact the Braskamp-Lieb polytope of these very simple projectors. So the matroid polytope is a Braskamp-Lieb polytope. That's a very simple example, but it's also a simple optimization problem. Here's a more sophisticated one, matroid intersection. That's already a non-trivial combinatorial problem. Here you have two matroids, M and N, and you are looking at a polytope which is the convex hull of sets of vectors that are bases in both of them. So this generalizes, for example, bipartite matching. So you want the convex hull of all these sets where there are a basis here and a basis here. And again, we knew, Edmonds knew, who solved this problem, knew what is a polytope here. And again, it's a Braskamp-Lieb polytope of a very simple projectors that I'm not going to define. Very natural and very simple. But again, we also have an algorithm for this. So what's a nice problem which has an exponential size linear program, and we don't know. We know how to solve, but we don't know how to solve this way. Here's my favorite. So I started with matching. I'll end with matching. Here's my favorite question in this. Is general matching, not bipartite matching, general matching, which is one of the combinatorial optimization problems which has the most sophisticated algorithm to date, and we don't have a simpler one. We have a graph on even number of vertices, and we are looking for a pairing of these matrices. Edmonds defined the matching polytope. So the matching polytope, again, you can take the convex hull of all perfect matchings, and determining the facets is non-trivial. And here are the facets. It's just like the matching polytope, except you have to have this, exponential many conditions saying that you cannot have a perfect matching on an odd set of vertices. So every odd set has an inequality here, and it's an exponential number of conditions. And I wish I knew if this is a Braskamp-Lieb polytope. That would lead to a completely different algorithm for general matching. Okay, so let me conclude. Of course, find other examples. So let me conclude at the last slide. Well, I mean, it's impossible to summarize such a talk, but what we've seen, I want to stress some general themes. So one is the important interaction of algorithmic questions with basic mathematical questions, and which led to lots of this progress. The ubiquity, in some sense, of this alternate minimization, the power of this very simple heuristic, and the natural way in which scaling algorithms arise both from optimization motivations and also out of the blue from invariant theory. The many incarnations over lots of fields of mathematics of the symbolic matrices and their singularity, both in the commutative case and in the non-commutative case. And one thing I particularly like, and I think is sort of has a lot of power, and we'll probably see more of it, is how analytic algorithms, dynamical algorithms, are useful to solve algebraically looking problems like singularity of symbolic matrices. And on the other hand, how these analytic matrices, in order to analyze them, to prove complexity bounds for them, we have to resort to algebraic methods, invariant theory, algebraic geometry, and so on. Open problems, lots of them, but they are the obvious ones. We didn't do anything for the commutative case, and we don't know the VP and VNP answer. I think that a very interesting direction that we just began to scratch the surface of is the power of these analytic algorithms in invariant theory. In some cases, we can bring down double exponential complexity to exponential. In some cases, we bring it even to polynomial. And there are lots of problems in invariant theory, lots of problems in other actions. And in fact, you'll hear from Ketan Murmuri other algorithmic questions in invariant theory, and I think these algorithmic techniques are useful. Better understanding of alternate minimization in general, and well, there are so many connections, probably there are more. So, thanks. Questions? Yeah.
Could you get back to that Matroid slide? It was like, yes, no, previous one. No, with Vishnoi.
Yeah, no, it's just.
This is just operator with rank 1 matrices.
Yes, you can. Yeah. This was known. Yeah, just in a paper we wrote, there was the proof we gave had the bug, and he fixed it. But yeah, it's simple. It's very simple. Yes. Yes. Sorry. More questions. Everybody's hungry. Okay.